Okay, so now we're going to do an example where we show that a function is a bijection. Of course, the bijection means that the function is injective and surjective. So we're basically just going to show those one at a time, right? You don't you don't try to show them at the same time. I'm going to not do much of a sketch this time, but let's just make sure that you understand how this function works. So if I plug in 2 comma 4, then I get 2 plus 2 times 4, and then we get 2 times 2 plus 3 times 4, right? Just plugging in the corresponding x and y's into the formula. And so what do we get here? We get 10 comma 4 plus 12 is 16. And also we can plug in negative values. So if I plug in negative 2 comma 1, I get negative 2 plus 2 times 1, and I get 2 times negative 2 plus 3 times 1. So we get 0 comma negative 4 plus 3, so that's negative 1. Okay, and you can plug in all kinds of different values here. So again, it's the integers cross the integers to the integers cross the integers. So we get all the negative numbers, 0, and all the positive naturals. And this is supposed to be a bijection. Now, it's a bijection. That means there's something special about the choice that I made, because meaning there's something special about x plus 2y and 2x plus 3y, because there are plenty of ways you could have defined the function where it would not be a bijection. Okay, so this has to have a special function in that sense. Okay, let's actually go right for the proof. I would encourage you to play around if you like with before watching me do the proof, but let's play around. So we'll start by showing f is a projection. So sorry, surjection. So maybe we'll just start by reminding the reader. So consider f from the integers cross the integers to the integers cross the integers defined by of x comma y is equal to x plus 2y and 2x plus 3y. We will show that f is a bijection. Okay, great. So to show that f is a surjection, consider any m comma n in z cross z. Now, the thing is a little bit funny about this is the domain and the codomain are the same. So it's not funny, that happens a lot. But that means when I say m comma n is in z cross z, I'm the one that needs to remember that I'm thinking about it as the codomain right now, because we're doing surjective. I need to show that for any element in the codomain, there exists something in the in the um, in the domain that maps onto it, right? So that's what I'm going to tell the reader. So now I'm consider any m comma n in z cross z and show that there exists a x comma y in z cross z, so that f of x comma y, which let's just remember is equal to x plus 2y comma 2x plus 3y, equals m comma n. Right? That's what I need to show. So I'm just reminding the reader of what I need to show, but it's also helping me to remember what I need to do here. And so, well, again, we have two ordered pairs equal to each other. So that means the components have to be equal to each other. So by equating components, we find the first equation, which is x plus 2y equals m, and the second equation, which is 2x plus 3y equals n. I'm going to call the first equation 1 and the second equation 2. Yeah, so basically what it boils down to here now is showing that there is a solution to this system of equations. So you may not have expected that, but to show that this is a surjection, I've reduced it down to showing that there is a solution to the following system of equations, where I think of m and n as data that's been prescribed to me. Someone has given me a specific m and n, and it's my job to tell them what the x and y are, so that when I plug them into 1 and 2, I'll get equal to m and n, right? Okay, so what I want to do now is solve the system, right? Right. So how do we do that? Well, there's a few ways we can do this, but in particular, I want to eliminate x. So notice if I multiply 1 by 2 and then subtract equation 2, I will eliminate x, right? So that's one way to try to do this. So let's do that, right? So by multiplying equation 1 by 2 and subtracting equation 2, we find, I'll let you write down more details if you like, but if you do this, you should find that when you multiply the first equation by 2, you get 2x plus 4y equals 2m. So you get the 2x subtracting the 2x, so that'll cancel out. You get 4y minus 3y, that'll just get you y, and then you'll get 2m minus n, right? So you find that y is equal to 2m minus n. So now we feel pretty good, but we're not done yet. We also need to know what x is, right? So now we know what y is. We could plug it back in, or we can try to eliminate y. It's kind of up to you what you want to do. But let's see, by plugging, maybe we'll just plug this in, plugging y equals 2m minus n into equation 1, we find, let me give myself some more room. So by plugging that in, we get x plus 2 times 2m minus n equals m. So we can solve this now. So we get x is equal to m minus 4m minus 2n, which is equal to what? M minus 4m plus 2n, which is equal to minus 3m plus 2n. So hence x comma y equals, I'll write this equals minus 3m plus 2n comma 2m minus n is a solution, so that if I plug in f of x comma y, I get what I was trying to start with, which I forget the order, m comma n, gives me m comma n. Hence, f is surjective. Okay, so I just want you to note that in order to show a surjective here, we boiled it down to solving a particular system of equations. And once we found that there was a solution, that is the thing that you plug into the function to map onto a particular value in the codomain, right? Okay, so now f is surjective. Now we want to show it's injective, right? So let me give myself room again. So now to show that f is injective, we consider two different values, so m1 comma n1, m2 comma n2, that are both in Z cross Z. But now I want to think about them in the domain, right? So the domain and codomain are the same. So I need to be the one that remembers how I'm thinking about this at different points in the proof. So right now I'm thinking about this as the domain, so that, and it'll be clear when I write down this next part, right? Because I'm going to plug it into the function. If I'm going to plug it into the function, it better be an element of the domain. Okay, so I want to consider two different values in the domain so that the image under the function is the same. And then I want to show now that that means that the two values that you thought were different in the domain are actually the same exact thing, right? Great. This is equivalent to, well, by definition, that says that m1 plus 2n1 comma 2m1 plus 3n1 is equal to m2 plus 2n2 comma 2m2 plus 3n2, right? That's just what the definition of the function is for these two different values. So then again, by equating coordinates, we find that m1 plus 2n1 needs to be equal to the first coordinate of the second order pair, so m2 plus 2n2. And we find that the second coordinate, 2m1 plus 3n1, must be equal to the second coordinate of the second order pair. All right, so now we again get a system of equations. Maybe I'll call this one 3, since we're still in the same proof, and 4. Okay, so we got a new system of equations, and now it's a little bit different though. It's not really the kind of equations we had before, because now there's only two variables, m1 and sorry, no, there's four variables. But what we want to show, what we're hoping, is that m1 is equal to m2 and n1 is equal to n2, right? So we'll see if that's the case. So, well, first of all, we need to eliminate some variables. So, there's a few things we can do. So we can see that we can eliminate m1s and m2s by multiplying 2 times equation 3 and subtracting equation 4, right? So now by multiplying 2 times equation 3 and subtracting equation 4, we find, all right, so what do we get when we do that? So we get 2m1 plus 4n1 equals 2m2 plus 4n2, and then we're going to subtract the equation as already written. And if you can see already what's going to happen, this kind of falls nicely in our lap. This is 0. This is 0, and what we get left over is just an n1 equals n2. Perfect, right? And now we need to do something similar, but I want to eliminate the n1 and n2. So now by subtracting equation 1 minus 2 times equation 2, we find, okay, so now if we do that, we're going to get equation 1 and then we're going to subtract 2 times the second one. So Oh, sorry. Oh, that's not what we want to do. So let's see. What do we want to do here? So I want to, what do I want to do? I want to eliminate n1, 2. So if I multiply the first one by 3, and let's do this again. So I want to eliminate n1 and n2 by subtracting 3 times the first one, right? So 3 times equation 1 minus 2 times equation 2, be fine. Well, what do we get? So we get 3 times m1 plus 6 times n1 is equal to 3 times m2 plus 6 times n2. And we're going to subtract here 4 times m1 plus 6 times n1 is equal to 4 times m2 plus 6 times n2. And of course, now we see that we get minus m1 is equal to minus m2, which implies m1 is equal to m2. So we have that m1 comma m2 must be equal to n1 comma n2, and hence f is injective, right? We started with what we thought were 2 different values in the domain whose image was equal, but then they wound up being the same. So therefore, f is a bijection. If you show that it's surjective and injective, then it's a bijection, right? Great, so that's a good example of showing something's a bijection, and it wound up boiling down to solving several different systems of equations.